Welcome to section 10.1, where we dive into the student's t-distribution, an essential tool for real-world data analysis when we don't know the population standard deviation. Let's say you're trying to estimate the average number of hours students at your college play Apex Legends per week. You collect a sample, but you don't know the population standard deviation, only the samples. That's where the t-distribution comes in. It lets us work confidently with small sample sizes and unknown variability. In this section, we'll explore how the t-distribution differs from the normal distribution, how it adjusts for smaller samples, and how we can use it for inference. By the end, you'll be able to use it for hypothesis testing and confidence intervals in the wild, whether analyzing gaming stats, student sleep habits, or Marvel movie runtimes. Let's start with the why. Why do we need yet another distribution, this mysterious t-distribution, when we already have the normal distribution we've been using? Here's the key. When we're working with large samples, say 30 or more, and we know the population standard deviation, the normal or z distribution works beautifully. It gives us tight, predictable probabilities and confidence intervals. But in real life, we rarely know the population standard deviation. And when we're working with small samples, the normal curve tends to underestimate the real uncertainty in our estimates. This is where the t-distribution steps in. It's wider and more forgiving. It accounts for the extra uncertainty that comes with estimating sigma from a small sample. Let's say From Software just released a new patch for Elden Ring, and you want to estimate the average time players are spending on the updated boss fights. But only 12 players have downloaded and played it so far. You don't have the full population standard deviation. You're just working with what those 12 people gave you. That small sample means your estimate is a little more volatile, a little less stable, and the t-distribution helps you adjust for that extra wiggle room. So in short, when n is small and the population standard deviation is unknown, we don't throw up our hands. We use t instead of z to make better, more accurate inferences. Let's meet the star of today's chapter, the student's t-distribution. It has a fascinating backstory. In 1908, a chemist named William Seeley Gossett was working for the Guinness Brewery in Dublin. Yes, the beer company. He needed a way to make reliable statistical inferences from small samples. For example, figuring out how much variation there was in the quality of barley used for brewing when only a few test batches were available. At the time, Guinness didn't want their trade secrets getting out, so Gossett published his work under the pseudonym Student. That's why we now call it the student's t-distribution. Even though Gossett was testing hops and alcohol content, the t-distribution today is used across all fields where we're working with small samples and unknown population standard deviations, which is extremely common. Imagine you're a developer at Epic Games trying to evaluate whether a new Fortnite weapon rebalancing patch is increasing player satisfaction. You only have feedback from 9 beta testers. You can't assume you know the population standard deviation. It's too small of a group. That's a perfect job for the t-distribution. In essence, the t-distribution gives us a way to do inference when data is limited and messy, which is basically always the case outside of textbooks. Here's the golden rule. Use the t-distribution when you don't know the population standard deviation and you're working with a small sample. Typically, n is less than 30. It's common in practice because full population data is rare. Think of it like analyzing how long Dune fans wait in line at the cinema. If you only surveyed a dozen people and didn't know the standard deviation for all Dune watchers, a t-distribution lets you draw conclusions with adjusted caution. The t-distribution is wider and flatter than the standard normal distribution. Why? Because small samples have more uncertainty. The t-distribution accounts for this by being more forgiving in its tails. Now let's talk about something that sounds abstract at first, but is actually really intuitive once you connect it to real life. Degrees of freedom, or DF. So what are degrees of freedom and why do they matter? Definition-wise, degrees of freedom for a single sample t-test is simply your sample size n minus 1. That's it. If your sample size is 10, your degrees of freedom would be 9. If your sample size is 25, your degrees of freedom are 24. But here's what that really means. Degrees of freedom tells us how much independent information we have to estimate something, usually the standard deviation. When we estimate the standard deviation from a sample, we're using up a little bit of freedom. Why? Because once you fix all but one data point, that last point is basically locked in. It has to fall in a specific place for the sample mean to be what it is. Let me give you an analogy you might relate to. Imagine you're working on a group project with 4 people. You all have to track your hours and report them. If 3 of you have already logged your time and the group total is fixed, that last person's hours aren't really free to vary anymore. Their value is already determined by the group average. That's why we subtract 1. Now, why does DF matter in the t-distribution? Because it shapes the curve. When DF is small, the t-distribution has thicker tails, meaning there's more probability out in the extremes. This reflects greater uncertainty in our estimates when we don't have much data. As DF increases, the curve flattens and becomes almost identical to the normal distribution. So, small n equals more uncertainty equals thicker tails. Large N equals more confidence equals Z-curve-like behavior. This is why statisticians get excited about big sample sizes. The math gets simpler and more powerful. Let's compare the Z-distribution to the T-distribution. The Z-distribution assumes we know the population standard deviation. Not likely in the real world unless you have massive clean data sets. The t-distribution, on the other hand, uses the sample standard deviation, and its shape depends on degrees of freedom, df equals n minus 1. Think of Z versus T like comparing a Marvel script draft to the final film. The draft Z is idealized and perfect. Everything is known, clean, structured. The t-distribution is more like the real film. Still awesome, but with real-world messiness accounted for. Let's take a real-world example. Suppose only 12 players tested a new Apex Legends map. That's a pretty small sample size, and we definitely don't know the population standard deviation yet. In this case, we can't rely on the normal Z-distribution because there's too much uncertainty. Instead, we use the t-distribution, which accounts for that extra variability and gives us a more cautious, realistic estimate. When n is small and sigma is unknown, t is the only trustworthy guide. As the sample size increases, the t-distribution approaches the z-distribution. Just like the more data you have, the more confident you can be. Now let's look at the formula you'll use over and over. T is equal to x bar minus mu naught over S divided by square root of n. X bar is your sample mean, mu naught is the hypothesized population mean, S is your sample standard deviation, and n is your sample size. This formula measures how far your sample mean is from the hypothesized population mean, scaled by standard error. The result is a t-score, like a z-score, but adjusted for sample size. Let's say you claim the average time students spend on Dark Souls each week is 6 hours. You take a sample of 15 players and find a mean of 7.2 hours with a sample standard deviation of 1.8. Plug those values in to compute your t-score and evaluate the claim. Now, let's pause for a moment and talk about the ground rules for using the t-distribution. Just like you wouldn't jump into a boss fight in Elden Ring without checking your gear and stamina, you can't just blindly use the t-distribution without checking a few key assumptions. Here are the 3 you need to remember. First, your sample needs to be randomly selected. This ensures that your data actually reflects the broader population. If your sample's biased, say you only surveyed your Discord server buddies about screen time, you can't trust your results. Second, the population should be normally distributed. This is especially important when your sample size is small. For example, if you're testing a new Apex Legends update with just 15 players and playtimes vary wildly, you might run into trouble unless you know the population distribution is roughly bell-shaped. Finally, the sample size should be small, typically under 30. That's where T really shines. For large samples, the central limit theorem saves us, and we can use Z. But when we're working with just a few data points, like a small beta test or early access reviews for a new Minecraft mod, we need the extra wiggle room. The t-distribution gives that to us. So remember, random sample, normal population, small n. If these conditions are met, the t-distribution is your hero. Let's walk through a complete example. You survey 12 students about how many hours per week they play Elden Ring. You find sample mean is 8.3 hours, sample standard deviation 1.5 hours, hypothesized mean 7.0 hours, and sample size 12. Using the formula, we would have our mean 8.3 minus the population 7.0 divided by the sample standard deviation 1.5 divided by the square root of n 12. We get about 3.0. With 11 degrees of freedom, n minus 1, we check a t-table for alpha equals 0.05. The critical value is approximately 2.201. So looking at our normal curve, lost my pen there. All right, looking at our normal curve, go back. There we go. I don't know why I'm having so much trouble drawing. Looking at our normal curve, we found the critical value on the table was approximately 2.201. So we're over here at 2.201. So anything bigger than that is in the rejection region. Well, we got a 3. That's way over here in the reject region. Remember, this is our fail to reject region over here. So we reject the null hypothesis. The data suggests students are playing significantly more Elden Ring than the average claim. All right, you're investigating whether a new Minecraft mod increases daily playtime. You collect a small sample of 10 players, and you find that they're averaging 3.8 hours per day. The standard deviation of this sample is 0.6 hours. The claimed average, or what the developer asserts, is 3.5 hours per day. So we're wondering, is this observed increase enough evidence to say the mod truly boosts playtime? All right, so we've got X bar is 3.8, S is 0.6, mu naught 3.5, N is 10, and our degrees of freedom is 10 minus 1 or 9. Our first step is the hypotheses. Mu equals 3.5. The average playtime is still 3.5 hours. Our alternative is mu is bigger than 3.5. The average playtime has increased. This is a right-tailed test. So again, we're looking at this as being our rejection region, and this is our fail to reject region. Because we're looking for evidence of an increase. That's why we're right-tailed. All right, now we're going to calculate the test statistic. So we get T is our sample 3.8 minus the population 3.5 divided by our standard deviation 0.6 divided by the square root of our sample size 10. Get about 1.58. So we look up to compare to a critical value. Look up 9 degrees of freedom, alpha equals 0.05. We find the critical value is about 1.833, which is here. We got 1.58, which would be over here. That's in the fail to reject region. So we would fail to reject the null hypothesis. All right, now our conclusion. Even though our sample mean is higher, the difference isn't large enough to be statistically significant. It could just be due to random variation. So while the mod might be increasing playtime, we don't have strong enough evidence from this small sample to confidently say it does. Think of it like this. If this were a new Apex Legends feature and your beta test squad showed promising playtime bumps, you'd still want a larger sample before making claims in the patch notes. Let's wrap up everything we've learned about the student's t-distribution. First and foremost, use the t-distribution when sigma is unknown and your sample size is small. That's the golden rule. If your sample size is under 30 and you don't know the true population standard deviation, the normal distribution just isn't safe. It assumes too much. That's where t comes in. It adjusts for that added uncertainty and keeps your conclusions honest. Next, t is like z, but more cautious. It protects you from overconfidence with limited data. The t-distribution has thicker tails than the normal curve. That's its way of saying, hey, your data might be a little more variable than you think. It's like putting on extra armor in Dark Souls when you're entering a new dungeon. You need that extra protection until you're sure what you're up against. Always check normality and sample size before using it. The t-distribution assumes that the population you're sampling from is roughly normal. With small samples, that assumption matters even more. Think of it like polling only 10 players about a new Elden Ring update. If their feedback is wildly different, your conclusions will be shaky. A normal shape helps smooth those risks. The smaller the sample, the wider the confidence interval, and the more careful we must be with our conclusions. Small samples mean more uncertainty, so your confidence intervals get wider. That's just statistics being honest with you. The fewer the data points, the fuzzier the estimate. Finally, remember this. Whether you're testing if a new Fortnite mod truly increases playtime, or if Marvel fans really spend more time in theaters than DC fans, the t-distribution is your tool of choice when your data is limited, but your questions are big. It keeps your inferences grounded in reality, even when you're working with just a few voices in the crowd.